In this chapter, we look at free energy and thermodynamics. So, what are these things? First, we start by talking about a spontaneous or non-spontaneous process. So, by definition, spontaneous processes need no outside intervention to occur. So you don't need to put work in them. You don't need to use external force on them. They are going to work without outside intervention. One example of a spontaneous process is if you drop a book. So dropping a book, the book goes directly down towards the floor. So the book is going to touch the floor. That is a spontaneous process. That is an expected process. If you talk about water, water will spontaneously go down a waterfall. So water is not going to be climbing the waterfall. So the expected way that water can go is just down a waterfall. So going down a waterfall is a spontaneous process. Now, we can talk about the same spontaneous processes in case of chemical reactions. But it's not obvious. We can't just say this reaction is spontaneous. This reaction is not spontaneous. We cannot guess. So in that case, we need a chemical potential. We need a chemical potential that will predict spontaneous. We need some characteristic that we are going to look at to tell us that this reaction is spontaneous, this reaction is not spontaneous. Now let's look at enthalpy. Let's look at a characteristic enthalpy. So does enthalpy predict whether or not a reaction will be spontaneous? Just look at the sentences. Some exothermic processes are spontaneous, but the focus is on some. So some exothermic processes are spontaneous. So we have examples here. If you go to below zero, the water will spontaneously freeze. So freezing is spontaneous. Freezing is exothermic because it releases energy. That's why it is exothermic. If you dissolve sodium hydroxide in water, your hand will feel warm. And the dissolution is quickly, right? So you have a quick dissolution. So sometimes you don't even need to stir. You just need to put the sodium hydroxide in water and it immediately dissolves, which means this process is spontaneous. The respiration reaction in the body or in the plants, in animals, it is spontaneous. You don't need to force it. It just happens. So we have seen that all these processes here are exothermic, but they are also spontaneous. But we are saying some exothermic processes are spontaneous. Not all. The same thing with endothermic. Some endothermic processes are spontaneous. Not all of them are. So what it means is you can't say because this reaction is exothermic, then it's spontaneous. Or you cannot say because this reaction is endothermic, then it's spontaneous. You also cannot say, because this reaction is endothermic, therefore it is not spontaneous. You cannot do that. Here we have seen two reactions or two activities that are endothermic, but they are spontaneous. So if you go above 0, water is going to melt. You don't need to force it. It just melts on its own, spontaneously. If you dissolve ammonium chloride in water and you touch the container will feel cold because ammonia is taking energy from your hand, which means dissolution of ammonium chloride is endothermic. But you know what? It happens spontaneously. You don't need to force it, although it is endothermic. So, what does this tell us? This tells us that we cannot use enthalpy to tell us whether a reaction is spontaneous or not. We cannot use enthalpy to tell us that. But now, if you cannot use a characteristic that we call enthalpy, so what other characteristic can you use to tell you that this reaction is spontaneous or not? We define a thermodynamic characteristic called entropy. So really, entropy is just a function, a thermodynamic function that increases with the number of energetically equivalent ways to arrange a component of a system to achieve a particular state. So enthalpy has a symbol S. S is given by a constant K times the natural log W. So this is the mathematical representation of entropy. So this is mathematical representation of entropy. So W there is a number of possible ways that we call microstate that can result in a given state. So when you talk about microstate, you define them in terms of pressure, that is P, volume, and absolute temperature. So the absolute temperature is given by Kelvin. We use Kelvin units for that. Now, let us see what we mean by macrostate versus microstate. Let's look at two systems. We have system A, we have system B. And let's look at the states of the systems. System A has a single state. So this one has one state, which means the only way we can arrange these two things are just by putting them here in this one state. System B has two states. So we can arrange these things here, we can arrange them here, or we can have one here, one here. So what I'm saying is system A has one state. System B has two states. And if we want, we can say system 1 has one microstate, system 2 has two microstates. So 1 micro state. This one has 2 micro state. What it means is that these two here have nowhere to go. They will be in just this single state. While these two, this one can come down here and we have 2 of them here and none here, or both of them can go up here and we have 2 of them here and none here, or one can be here, one can be here. So this one has a number of states that an object can find itself in. So what does it mean? In terms of W, this one has a bigger W. Has a bigger W because it has more micro states. This one has a smaller W because it has less microstate. In that case, we'll say that B has higher entropy because it has more micro states. So the more the microstate, the bigger the W, the higher the entropy. Now let's go deeper into these microstates. Let's look at 3 systems. So we have a container which is divided into 2 containers, and we have a tubing like this tubing here. We have a tubing that connects the containers. So all of them have a tubing connecting the 2 containers. Now, in A, we make a restriction. In state A, we make a restriction. All our particles are in one container. So they are restricted to this container. So this is a macro state. That's what we see. We see that the particles are in one container. In B, the particles are in the second container. So we can say this is macro state of A. That is a state that we can see, or an average state of a substance of these particles in there. This one is macro state of B. That is the average state of B. So what we are saying is we can look at that and say, oh, the particles, the gas particles, are in the right side container just by looking at it. And C gives us macro state C. So we can just look at this and say, you know, 2 particles are in the right side container and 2 particles are in the left side container for C. So we can just look at this and say these are the macro state. Now, each of these macro states is going to have its own microstates. So what we are going to do is to look at A and see how many microstates is it going to have. We do the same thing with B. We'll look at B and say how many microstates is B going to have. Then we'll look at C and see how many microstates is C going to have. So let's move on and look at them. Starting with A here, we see that the only place or the only side we can find these 4 gas particles is just in the left container because we have restricted here. The gas particles cannot go to this side. So the gas particles cannot go to this side. They will always be found in this side. So although this is a macro state of the gas particles here, because we don't have any other state where we can find these gas particles, they are restricted. This macro state will also just become a micro state. So there is one macro state and also one micro state. So what it means is there is only a single way that we can find these gas particles in this container. Only a single way. So that single way is a micro state. What about B? The same thing. This is the macro state, how the gas particles are viewed. If you look at this container, we will see these gas particles in here like this. And we say that is a macro state. But then, let's look at the micro state. How many ways can we arrange these gas particles, especially with this restriction here? There is only one way that we can arrange these particles. So because there is only one way, this one also has one micro state. So we say here one micro state of the particles, one micro state of the particles. One macro, this one should be macro, not micro. One macro state of these particles here, also one micro state of the particles. So that is between A and B. Now let's go on to look at C and see how many micro states we can have from the macro state of C. So for C, this is our macro state. So if you are looking at these containers, you can say that I have 2 particles on the left side, I have 2 particles on the right side. So that is the macro. That's the average, how they are present in those. But now you can say, yeah, although I have 2 particles in the container, but they can be found within different locations in those containers. Like they can be found here. These 2 particles can be found here at one point. That becomes a macro state. Or they can be found here at another point. That becomes another macro state. Or the 2 particles can be found one here, one here. That becomes a third macro state. The same thing here, one macro state where the particles can be found, because the particles move around. The particles can be found here. The particles can be found here. So this is what we are showing this side. So although we have 2 particles in here, 2 particles in here, but because we are giving them more freedom, we are not constraining them, they can be found in different places within a single container. They can be found up here or down here. So in this case, this one is up, this one is down. That is one macro state. Or they can be found like this. That is another macro state. Or they can be found like this. That is a third macro state. They can be found like this. That is a fourth macro state. They can be found this. So you can see that here, if we stop constraining the container, we have more microstates that these gas particles can be found. So in terms of entropy, the entropy of A is equal to the entropy of B, because both of them have one microstate. But the entropy of C is greater than the entropy of A and the entropy of B, because as you can see here, C has 1, 2, 3, 4, 5, 6, has 6 ways of arranging things. So C has 6 ways of arranging the gas particles. So what it means is C has the highest entropy. That's what it means. It has a lot of microstates, therefore it has higher entropy. Now, entropy is a state property. So entropy is a state property, which means it depends on initial and final. So depends on initial and final state of a system. So because entropy is a state property, we can use delta S. We can use delta S to give us the change in entropy. And the change in entropy is given by the final entropy, S final, minus S initial. So S final is entropy of a state in which atoms are distributed between the two flasks, while S initial is entropy of a state in which atoms are in one flask. Normally, S initial is the entropy at the beginning, while S final is entropy after some time. So that is the equation for entropy. Now, when you look at entropy and the state of matter, when you compare solids, liquids, and gases, solids are constrained. Solids are constrained. Therefore, they have low entropy. Liquids are less constrained than solids. Therefore, they have higher entropy. They have higher entropy than solids. While gases are the least constrained. That is, they can move freely without any constraints. Therefore, they have the highest entropy. So a gas has so many ways that it can move. It is not constrained by a certain ionic interaction or the three-dimensional structure that we see in solids. Gases do not have that. So if you compare the same thing like water, we'll say that ice has less entropy than liquid water and has less entropy than water vapor. That's what we are showing here. So gases have higher entropy than liquid, which in turn have higher entropy than solids. Now, this whole discussion is to find out the way that we can say that this reaction is spontaneous. This reaction is non-spontaneous. That's the whole discussion. How do we do that? The second law of thermodynamics gives us a clue. What does the law say? The second law of thermodynamics says that entropy of the universe increases in a spontaneous reaction and remains constant in an equilibrium reversible reaction. So entropy of the universe, that is the whole universe, increases in a spontaneous reaction and remains constant in an equilibrium reaction. So for that, we'll say delta S, the change in entropy of the universe, delta H universe is equal to or greater than 0. So greater than 0 means increases. Equal to 0 means it is constant. So how will we know that this reaction is spontaneous? For us to know that the reaction is spontaneous, we use the entropy of the universe. So the entropy of the universe will tell us that this reaction is spontaneous. How? If the entropy is greater than 0, then the reaction is spontaneous. So we will say that delta S univ 0, that is spontaneous. Delta S univ is equal to 0, that is reversible. But what is this entropy of the universe? What is this delta S univ? So the delta S univ is given by 2 delta S. So if you have a chemical reaction and you are doing a reaction, the reaction will have an entropy that we'll call entropy of the system. So entropy system, sys. But as the entropy of the system is occurring, there will also be an entropy of the surrounding, because each system has its own surrounding. So entropy of the universe is the sum of the entropy of the system and the entropy of the surrounding. So by definition, the entropy of the universe is composed of entropy of the system and entropy of the surrounding. So delta S univ is equal to delta S system plus delta S surrounding. Now, this is the criterion to tell us that the reaction is spontaneous. Most of the time, one of the entropies, system and surrounding, will be rising and the other will be one will be greater than 0 and the other will be less than 0. As you can see here, if this is 0, if this is 0 point of entropy, you see here the system, entropy of the system is less than 0, entropy of surrounding is greater than 0. So let's say the entropy here is, let's say, plus 80 joules per Kelvin, while the entropy here is minus 58 joules per Kelvin. So as you can see, these are the units of entropy, joules per Kelvin. So units of entropy, joules per K. So if you add these two, so delta S universe is equal to minus 58 joules per Kelvin plus 80 joules per Kelvin. And from there, the entropy of the system will be 22 joules per Kelvin. So having a positive entropy means this reaction is spontaneous because you have a positive entropy. So if you are given a graph like this one, this side is entropy, then you have universe, you have system, you have surrounding. But this is our general equation. Entropy of the universe is given by entropy of system plus entropy of surrounding. Now again, just talking about spontaneous versus non-spontaneous reaction. In this case, we are talking about freezing water. Now let's look at freezing water at different temperatures. Let's look at it at low temperature. Let's look at it at high temperature. So at low temperature, if you try to freeze water at low temperature, what happens is, as the because you are doing the activity at low temperature, entropy of the system is going to be low because that is low temperature, as the system is releasing energy. So look at it. You are decreasing temperature of a system and the system is freezing. Freezing is an exothermic reaction, and exothermic reactions release energy. But your surrounding is at low temperature. So what happens is the energy that the freezing is releasing, it goes on to increase entropy of the surrounding. So the freezing releases energy, the surrounding is already at low temperature. When this energy is released, it goes on to increase the entropy of the surrounding. So what happens is the entropy of the system will be less than 0, the entropy of the surrounding will be greater than 0. When you add the two, the entropy of the universe will be greater than 0. Therefore, freezing water at low temperature is spontaneous. It just happens. But now let's think about it. You are freezing water, but at 50 degrees Celsius. Is it possible? It is hard. So as you are freezing the water at 50 degrees Celsius, what's going to happen is, the system is going to lose energy because you are freezing, you are releasing energy. The only problem is the surrounding is already hot. So the surrounding is already hot. Even if you add energy there, the surrounding is already hot. It's not going to change much. The entropy of the surrounding is not going to increase much because the surrounding is already hot. It's already at 50 degrees Celsius. But the entropy of the system decreases because your water is losing heat to the surrounding. But the surrounding is saying, you know, I'm already hot, I'm already disordered, therefore I don't need to disorder more. My entropy is already up, I don't need to change much. So what's going to happen is the decrease in the entropy of the system will be much higher. The decrease in the entropy of the system will be much higher than the increase in the entropy of the surrounding. So if the system here decreases by, let's say, minus 80 degrees, minus 80 joules per Kelvin, and the surrounding increases only by maybe 50 joules per Kelvin, what will happen is the entropy of the universe will be negative. So this one will be negative 30. But we know that for a spontaneous reaction, the entropy should be positive. Therefore, this reaction is non-spontaneous. So freezing water at high temperature is non-spontaneous because entropy of the universe is negative. The entropy of the universe is negative, therefore the reaction is non-spontaneous. So I'll continue this in my second video.